You have learned how to find the eigenvalue and eigenfunction by consider the initial and boundary condition. Once you find the solution for these three cases, you need to perform the superposition principle to find the total solution, which is the total solution for the first case, where you have xt function, plus the second case and the third case. In this step, you may need to apply the half-range Fourier cosine expansion, or the half-range Fourier sine expansion, or the full-range expansion in order to find the unknown coefficient. Let's solve an example for the 1D heat equation by applying these 5 steps. In this example, we have a heat equation that defines the heated root here. The length of the root is given from 0 to L in the x dimension, and you are going to find the temperature, which is given in U, with respect to x location here, and change with respect to time. The initial temperature is given, which is equal to fx function. This means that at time equal to 0, the temperature at various x locations at time equal to 0 will be equal to x function. So this is your initial condition. For example, if the fx is equal to x, then you need to substitute the x function with respect to the ux0 function here. So x function, let's start from 0 until L. Let's say you have 0, 0.1, 0.2 and so on until the total length L here. And then you need to substitute inside x here to obtain your ux0. So substitute 0 inside, you obtain your temperature equal to 0 as well. Substitute 0.1 inside, you obtain the temperature equal to 0.1 and so on. Therefore, you obtain the temperature distribution in such a way that at this point, this is your x equal to 0, so your temperature will be equal to 0. At this point, the temperature is equal to L. Therefore, you can assume this is the temperature, which is equal to the magnitude of L here. So you can see the temperature increase in a linear pattern over the time if you select your fx equal to x here. Now you should have a better understanding for the initial condition here. If we select the initial temperature equal to the function in terms of x, then in this case, the temperature is depend on x dimension. The initial temperature here is no longer equal to a constant here. So from this fx function, it can be any temperature distribution based on the function given here. The ends of the root are maintained at temperature equal to 0 at all the time when t is greater than 0. So at t greater than 0, you have the temperature at the end here equal to 0. At this position, you have x equal to 0. Therefore, your temperature at x equal to 0 for any time t will be equal to 0. So this is the boundary condition here. And then over here you have x equal to L. Therefore, the temperature at x equal to L at any time will be equal to 0, which is this boundary condition. Based on the given boundary condition and initial condition here, we are going to solve this PDE to obtain the temperature at all the x location at all the time. From the heat equation here, the dependent variable is U, independent variable are the x and t. In the step 1, based on the separation of variable method, we need to let the solution equal to the multiplication between the function of the independent variable, which is the x function, multiplied with the t function here. This can be simplified into capital X and capital T to indicate the x function and t function. Be careful, capital XT here are function and they are not constant. K is a constant, and then differentiate U with respect to x twice. So you need to differentiate this twice. So this is after you differentiate the u with respect to x1. If you differentiate u with respect to x twice, then you obtain x double prime t, which is this answer. Then differentiate u with respect to t, you obtain xt prime. T you move to the right hand side, you obtain t prime divided by t. X you move to left hand side, you obtain x double prime divided by x. Normally we keep the x double prime and t prime here, which is the highest derivative on both sides, to be 1. Therefore, this constant we move down here to obtain kt. So this is the result for the separation of variable, where you can see on the left hand side you only have x function, on the right hand side you only have t function. After that, you let it equal to a separation constant, which is equal to negative lambda. Don't forget the negative here. With that, you have 3 components here. Let the second component equal to the third component. Then you rearrange it, you should obtain this equation. And then let the first component equal to third component, you obtain this ODE. With that, we success to separate 2 ODE from the PDE here. So this is the 2 ODE that we obtain from this PDE. Let's consider 3 cases. First of all, we have the lambda equal to 0 in the first case. So you need to substitute 0 to the lambda here, then you obtain these 2 ODE. Since these are the homogeneous ODE, therefore we can use the characteristic equation approach to solve it. So for the first equation here, our t is equal to the exponential of the root multiplied with the t. T prime can be converted to the r. On the right hand side you have 0, therefore the root is equal to 0. Substitute the root inside this solution, you obtain exponential 0t. So this can be equal to 1, therefore your t is equal to a constant. The solution for the second ODE here is the x function equal to the exponential root multiplied with x. So you can convert this ODE into r squared equal to 0. From here, you have double root, therefore you obtain the first root equal to 0 and second root is equal to 0 as well. This is known as repeated root. Substitute inside this solution, you obtain the first solution equal to exponential 0x, second solution equal to exponential 0x, which are dependent to each other. Therefore, you need to do a treatment for the second solution here by multiplying the independent variable, which is the x. So in this case, you have the total solution equal to the superposition of these 2 solutions. Exponential 0 here is equal to 1, therefore you obtain c2 plus c3x. With that, we success to obtain the first PDE solution, which is equal to the x1 multiplied with t1. So substitute inside this parameter, then you obtain this. So multiply it with the c1 here, then you obtain 2 new constants, which is a1 and b1. For the second case, you need to substitute the lambda equal to negative alpha square, where the alpha is greater than 0. After you substitute inside here, you should obtain these 2 ODE. Similarly, these 2 are homogeneous ODE, therefore we can use the characteristic equation approach to solve this problem. You should be able to convert the t prime into r and negative alpha square kt into negative alpha square k. So this is equal to 0, and you can find the root equal to alpha squared k. So substitute the root inside the solution here, you obtain the t function equal to a constant multiplied with exponential with the root multiplied with t. By using the same approach, you can convert x double prime into r squared, negative alpha square x into negative alpha square. Therefore, you can obtain the root equal to this, and after you compute, you obtain the root equal to plus minus alpha, which is in the real number. Therefore, the solution for this ODE is in the function of hyperbolic cosine and hyperbolic sine. Multiply the x and t solution here, then you obtain the solution for the PDE in the second case, which is equal to this. So the constant C4, C5 and C6 here can be simplified into A2 and B2. For the third case, you have the positive lambda, which is equal to alpha squared, where the alpha is greater than 0. Substitute this into these two ODE, then you should obtain this result. And then you solve these two ODE separately. So for the first ODE, let the t solution to be in the exponential format, and you can use the characteristic equation by convert the t prime into r, alpha square kt into alpha square k. So from here you can find the root r to be this answer. Substitute this into the solution here. You obtain the t in the constant multiplied with the exponential with this root multiplied with the t. This is the solution for the second ODE. Then you can convert the x double prime into r squared and alpha squared x into alpha squared. Therefore, you can obtain the r to be this. Solve this, then you obtain the root equal to plus minus alpha I. Since this is imaginary number, therefore we can obtain the final solution for this ODE to be the cos and sine format. Multiply the x with the t here, then you obtain this solution where the C7, C8 and C9 here can be simplified into A3 and B3 constant. So this is the solution for the PDE in the third case. So far, you have success to obtain two ODE from this PDE, and then you assume the lambda to be three cases, 0, negative value and positive value. Then you success to obtain the t solution and the x solution for the first case, similar to the second case and third case here. After that, you know that your solution U1 is in the multiplication for the x function and t function. Therefore, you substitute this inside, you can obtain the first PDE solution to be this answer, and this is the solution for the multiplication between xt here, which give you this answer. Lastly, multiply these two, give you the third solution for the PDE. These are the given boundary condition and initial condition for the PDE. Let's apply this condition to find the eigenvalue and eigenfunction for each case. In the first case, where we let the lambda equal to 0, you obtain the PDE solution in this format. Let us apply this boundary condition. When your x is equal to 0, your u will be equal to 0. Therefore, let's substitute the x equal to 0 inside here. You obtain your u1 equal to b1. So, in this case, your u will be equal to 0. So this can be cancelled. Therefore, you obtain your b1 equal to 0. We can substitute back inside the PDE solution here to obtain the new PDE solution equal to a1x. Let's apply the second boundary condition here. When your x is equal to L, your u will be equal to 0. So substitute the x equal to L inside, your u will be equal to 0, which is equal to a1L equal to 0. So over here, since L is the length, therefore this can be equal to 0. Therefore a1 here must be equal to 0 to make this term equal to 0. Since your a1 and b1 are both 0 here, substitute inside, you obtain your first PDE solution equal to 0. That means there is no solution for the first case. This is the PDE solution for the second case, where the lambda is equal to negative alpha squared and alpha is greater than 0. Let's apply the first boundary condition. When your x is equal to 0, your u will be equal to 0. So substitute your x equal to 0 inside. Then you obtain your u equal to 0, which gives you this equation. So you have the exponential function here, and you have 0 on your right hand side. So you can assume there is exponential function here as well. Let's compare these two coefficients for the exponential function on these both sides. So we take out the exponential function on your left hand side. You have the hyperbolic cos and hyperbolic sine term. On your right hand side, the coefficient is 0. Hyperbolic sine 0 is equal to 0, therefore this term can be cancelled. hyperbolic cos 0 give you 1. Therefore, you obtain A2 equal to 0. Substitute A2 equal to 0 inside the original PDE here. You obtain this PDE solution. Let's apply the second boundary condition. When your x equal to L, you get the u equal to 0. Substitute inside here x equal to L and your u will be equal to 0. So this gives you this equation. We can compare the coefficient for the exponential term here in both sides. Then you have the hyperbolic sine term equal to 0. Let's look at this component. You have alpha L, where the alpha is greater than 0. So if you multiply the alpha with L, since the L is the length, which is positive, so you should obtain greater than 0 as well. So we know that alpha L is positive value. So this is the graph for the hyperbolic sine. When you take the hyperbolic sine on a positive value, then you are actually looking the value for this region, which is always positive over here. Therefore, when you take the hyperbolic sine for a positive value, it will be always greater than 0. And from the graph, you can see that it's not equal to 0. Therefore, this term is not equal to 0. To make the whole term here equal to 0, then we need to take the B2 equal to 0. Substitute the A2 and B2 inside this solution. You can cancel these two terms, which give you 0. 0 multiplied with exponential, you still obtain 0. So the PD solution here is 0, which means there is no solution for case 2. This is the PD solution for the third case, where we let the lambda equal to positive alpha square and the alpha is greater than 0. Let's apply the first boundary condition. So you have the x equal to 0. To make the u equal to 0, you substitute the x equal to 0 here, then substitute the u equal to 0 from here. With that, you obtain this equation. You compare the coefficient for the exponential term on both sides. Then you obtain the cos and sine term on the left hand side and 0 on the right hand side. Since you know sine 0 gives you 0, this term can be cancelled. Cos 0 gives you 1, therefore you obtain A3 equal to 0. Substitute the A3 equal to 0 in the original PDE solution here, then you obtain your new PDE solution. Let's continue to apply the second boundary condition here. When your x is equal to L, then your u equal to 0. When your x is equal to L, your u will be equal to 0. Therefore, you obtain this equation. Compare the coefficient for the exponential on both sides again. You obtain the sine term equal to 0. Let's look at this component, alpha L. Since the alpha is greater than 0, so alpha L will be greater than 0 as well, which means it's positive value. Since alpha L is positive, therefore when you plot the sine alpha L, we only consider the positive region. When you check the graph here, you can see that the sine alpha L can be equal to 0 at these few locations. And continue. This location is pi, this is 2 pi, this is 3 pi, 4 pi, and so on. From here we can see that sine n pi is equal to 0, where your n is equal to 1, 2, 3, and so on. When you compare these two equations, then we know that the alpha L is equal to n pi, which is this. And from here you can obtain your alpha, which is equal to n pi divided by L. Since the sine alpha L can be equal to 0 when the alpha is equal to n pi over L, therefore the B3 will not be equal to 0 here. Therefore you can substitute the alpha inside here. Since the B3 is not equal to 0, therefore you obtain the solution for the PDE here. So the solution exists for the third case, and this is your solution. Since you have multiple solutions from n equal to 1 to infinity, therefore you have n PDE solutions, where you can see the alpha here are substituted by the n pi over L, which is obtained from here. So far, you obtained 0 PDE solution for the first case and second case. There are no solutions for these two cases, therefore there are no eigenvalue and no eigenfunction. You obtain infinity solution for the third case, where you know the alpha is equal to n pi over L. Substitute the alpha inside this equation, then you obtain the eigenvalue, and the eigenvalue, which is the lambda, is equal to alpha squared, which is equal to n pi divided by L power of 2. Eigenfunction of the PDE means the solution of the PDE, which is equal to this. From these two formula, you can obtain the eigenvalue and eigenfunction in many modes. For example, at mode 1, your n will be equal to 1, then your lambda 1 will be equal to alpha 1 squared, which is equal to pi divided by L power of 2. And the corresponding eigenfunction is equal to U31 equal to the exponential negative n pi over L. So substitute the n equal to 1, you obtain pi over L square, and then kt remain. So v3n here become the coefficient v31, and you have the sine pi over Lx. So you can substitute the n equal to 2 inside to obtain the corresponding eigenvalue and eigenfunction. So you can continue up to n mode, where the n is from 1 to infinity. In step 4, you need to perform the superposition principle to find the total solution for PDE by combining the solution obtained for the first case, second case, and third case. So for the first case, you have 0, you can substitute. Second case, you have 0. Third case, you have this in the sine term. So after you substitute inside, you have the summation of the U3 solution here from n equal to 1 to infinity. So this is the total solution. You can expand this solution by substitute the n equal to 1 inside, you obtain the first component. Substitute n equal to 2 inside, you obtain the second component, and so on. You need to be careful, this is not equal to this total solution here. The total solution here has additional component for the summation here. This solution is just the individual solution when n equal to 1, which means this is the mode 1 solution. When n equal to 2, which means this is the mode 2 solution, and n equal to 3, 4, 5, 6, and so on until infinity. Total solution here, apply the superposition principle to take the summation of all the individual solutions. So the summation here basically is to apply the superposition principle, and it's very important. So don't just remain your solution in this format. This term and the total solution here are two different concepts. Therefore, you should proceed to apply the superposition principle to obtain the total solution. You success to obtain the total solution to be this answer, but yet there is still unknown coefficient here to be solved. Let's continue to apply the initial condition to solve this problem. So in this case, you have the t equal to 0, then you obtain the u equal to fx. Substitute the t equal to 0 inside, so exponential 0 give you 1, and the whole term here will become fx. Therefore, you only have the summation, the sine term here, equal to fx. So this is the new equation. And your x has a finite interval from 0 to L. So how can we obtain the coefficient here? In fact, you have learned how to solve this coefficient by using the Fourier series expansion technique. Let's recall the formula for the half-range Fourier sine series expansion, where you have the fx function in the summation from n equal to 1 to infinity, and you have a constant and multiply with the sine term in the bracket of n omega x. When you compare these two equations, you found that both of them have the same format, where the omega is equal to pi over L. When you compare these two components, to solve the coefficient for this PDE, it's very important for you to recognize the Fourier series expansion type. So in this case, you have the summation sine term on the left hand side only. Therefore, this is half-range Fourier sine series expansion, and we are going to use the corresponding formula to find the coefficient. This is the formula to find the Fourier coefficient here, based on the half-range Fourier sine series expansion. From the finite interval here, the maximum finite interval is equal to L. Therefore, we know that the tau is equal to L. You need to be careful. The L that we use in the PDE here means the length. But L over here means the half period, which is equal to P divided by 2. Since you are applying the half-range expansion, therefore the half-range for the period will be equal to the tau. And your tau is equal to L, you can substitute inside. So L is your length. And period divided by 2 is equal to the half period. So half period is L. So you can see that the half period here is same with the length for this particular case. It might be not true in other case. So you better check this. Continue from here, you can obtain the omega equal to 2 pi over P. So the P is equal to 2L here, which gives you pi over L. This is same with the omega answer that you obtained previously, so you can use either way to obtain it. So you substitute the tau to be the L, and substitute the omega to be pi over L. Then you success to obtain the answer for the B coefficient. So in this case, the fx and the L are not given. If these two are given, then you can find the value for this B. Once you success to find the B coefficient, don't forget to substitute back to the PDE solution here. So after you substitute this, you should obtain this result. This is the particular PDE solution that we are looking for, where you want to find the temperature at the X and T location. You just substitute the desired X and T into this formula, then you can find the corresponding temperature.